The next topic I'm going to talk about root locus method. So root locus is basically it is a powerful tool for adjusting the location of a closed loop pole to achieve the desired system performance. So basically it tells us how I mean where to put the poles, okay, or it tells us which will give you best performance by keeping the poles at which point. We know that as long as that's a real axis and imaginary axis, as long as poles are on this side, the system is um, stable. But at the same time, it's not only stability, the performance of the system is also important. Whenever you are moving away from this y-axis, that system is more stable. Okay, so if you're further away, that system is more stable than this pole right here. Okay, so root locus helps us to find the pole location. Now for example, if you take h of s equal to s square plus s plus 1 over s square plus 4s square plus ks plus 1. Okay, so here k is a variable. Now by changing the k value, we are changing the location of the poles. Okay, so here if you look at this graph, okay, so if I take k equal to 0, this is the equation. If k equal to 1, this is the equation. K equal to 2, that's the equation. Based on these numbers, okay, or equations, so based on this cubic equation, basically we can find how the system behaves by changing the k value. So for each k value, I mean, since it's s cube, you're going to have 3 poles. So these are the pole locations. Now whenever you have pole there, most probably you're going to end up another pole there, pole here, pole there, another pole here. So how the system is changing by changing the k value, how the system is behaving, or how the pole location is changing by changing the k value, that's what we can find out by using root locus. These lines are called loci. Okay, I'll talk about it in a minute. So connecting all these points in S-plane together is a drawing of how the poles are moving through the S-plane by varying the k value. That is called root locus method. So here, say for example, a waveform has e to the power of st. Now if you take s equal to -1, okay, this is the graph. See, it's going to take a little longer to settle down. If I take s equal to -3, it will settle down faster. Okay, now if you have s value as a positive, it's going to be exponentially increasing, so it will not settle down. So that's the reason if you have a pole on right hand side of this y-axis, that's unstable. Okay, now, okay, so if the s value is further away from origin on the left hand side, the faster the signal decays. So that means it's going to settle faster. If s value is positive and further away from the origin, then the exponential growth is faster. So as I mentioned, if it is further away, it's more unstable. Imaginary poles represents the sinusoidal motion, and imaginary poles are always comes in pair, complex conjugate of one another. Okay, if a system has imaginary poles, definitely those imaginary poles are always complex conjugate. So if one pole is say 2 plus j4, definitely we'll have a pole of 2 minus j4. Both poles are complex conjugate. Further the poles from the real line, then faster the oscillations. I'm talking about most probably to the on this side, on the right hand side. So if you have poles from the real line further away, faster. I'm sorry, so this is the real axis here, that's the imaginary axis. So if you have poles away, further the poles from the real line, then faster the oscillation. So if you have poles, say here is one pole, another pole is here, because that's a complex number. So if you have pole there, definitely another pole is going to be here. So if if you look at these two poles and another two poles here, okay, this system uh, oscillations are smaller compared to this system. Okay, our oscillations are faster for the system which has poles away. Complex poles represents both exponential and sinusoidal. I mean, imaginary poles represents only sinusoidal motion. If you have complex poles, then it is going to represent both exponential and sinusoidal motion. So if you have a system, it has both zeros and poles. Okay, both poles and zeros are responsible for the system character for forced input. Okay, um, poles are responsible for unforced input, as well as poles are responsible for the stability of the system. Knowing the location of the poles in S-plane not only find the stability of the system, but also whether response will be oscillatory motion and what frequency, and uh, is it exponential response or what rate. That will we can find out by knowing the location of the poles. Now, when you're choosing the poles, where do you want to choose the poles? As I mentioned, it's always on the left hand. This is the origin. Okay, so that point is 0. But further the poles from the origin, then faster the decay is. So, I mean, if you have poles away from the origin, that's more stable. So always choose in this area. And to have less damping ratio, we have to choose the poles in this shaded area. Okay, roots are nothing but the poles. Now here explaining about a small mechanical system. So yep, now I'm going to talk about the root locus and rules in the next video. Thank you.